Hello everyone, so in this lecture we will study about Kirchhoff law and combination of cell. So let's start from Kirchhoff current law. So Kirchhoff current law says algebraic sum of the all currents at a node is 0. So suppose we have a circuit, part of the circuit. Suppose in this branch current is I1 coming to the node, in this branch coming to node current is I2, in this branch current is going from the node current is I3, and in this branch current is I4 suppose, and let's take one more branch, current is coming I5. So sum of the all currents, algebraic sum, so I1 plus I2. Now I3 will be taken minus I3 because it is leaving the node. Similarly I4 plus I5, this will be 0, right? Or we can write current I1 plus I2 plus I5 equals to I3 plus I4. So we can say current coming to a node, sum of all currents coming to the node equals to sum of all currents leaving to the node, right? So we can say कि entering current equals to leaving current at a node. Now this Kirchhoff current law is based on conservation of charge. Right. Actually current, what is the current? Current is Q by T. Now here चार्ज, जो भी चार्ज T टाइम में आ रहा है वही चार्ज T टाइम में लीव करेगा. दैट मीन्स बिकॉज चार्ज नाइदर क्रिएटेड नॉर destroyed. That's why the total charge will be the same. So जो भी चार्ज इस नोड पर आ रहा है वही चार्ज इस नोड को लीव करेगा. That's why the current coming to the node equals to current leaving the node. Now based on this we will solve a simple question. So in this question we are given R1, R2, R3 values are given. Similarly 0.1, 2, 3 voltage are given, and we have to find the current through R1. So suppose this point, this is the node. Here suppose voltage is V and current in this is I1, current in this I2, both current are leaving, so current coming to this node will be I3. Here we can write simply current leaving to the node equals to current coming to the node, right? I1 will be V minus V1 upon R1 plus I2 will be V minus V3 upon R3 equals to I3. This will be V2. Actually consider this like this. This is R3 no? So this will be I3 and this will be I2. Suppose this is I3 and this is I2, so equation will change. I1 plus I3 equals to I2. So V minus V3 upon R3, and this will become equal to V2 minus V upon R2. Now if all values V1, V2, V3, R1, R2, R3 are given, so we can find the value of V from here. Now the current in R1 will be V minus V1 upon R1. Now second law is Kirchhoff voltage law. So Kirchhoff voltage law say algebraic sum of changes in voltage, or we can say changes in potential around a closed loop. Will be 0. Right. So suppose take a simple circuit which have a resistor and a battery. Suppose this voltage is V and this will be the high voltage and this will be the negative or low voltage end. Suppose current is flowing I in this circuit, it will flow from low voltage to high voltage for resistor. Now current flowing in this resistor will be also I. So here for this closed loop we can write, if we start from point A and then point B, then point C, then point D. So if we start from A, B, C, D, A. So from starting A to B we can write plus V, then in CD branch it will be minus I into R equals to 0. This is the Kirchhoff voltage law. So we can say V equals to IR for this loop. Now always remember, for a resistor, if current is flowing in this direction and we are also moving in this direction, then we will write minus IR, right? If we are moving opposite to the current direction of current, then we will write plus IR. Now suppose there are more than one resistor in closed loop. Suppose this resistor is R1, this resistor is R2, this resistor is R3, this battery is suppose V1, this resistor is R4, there also a battery, this is V2. Now if we move from here and current will be same in this whole loop, so Kirchhoff voltage law will be, if we start from here and if we move in this direction, suppose current is in this direction and current is I, then starting from here minus I into R4 plus V1 minus I into R3 minus I into R1 minus I R2. Here we will write minus, not plus, minus V2, because we are moving from high voltage to low voltage for this battery, and this will be equals to 0. Now based on this we will solve a simple question. Calculate the voltage across 10 ohm resistor, right? So we can calculate easily applying to the Kirchhoff voltage law. So first of all remember these 2 points. For a battery, if we move from a low voltage to high voltage, if we are moving in this direction, then we will write plus V if voltage of this battery is V. And if for a resistor R, current is in this direction and we are also moving in the direction of current, then we will write minus I into R, right? Now for this circuit, suppose current is I, then we will write, if we are moving from this point, A point, then we will write plus 12 because we are moving low to high voltage. Then current, for this current direction will be like this, because current is flowing already given in this direction, then in this direction, then here in this direction. So we will write minus I into 5. Similarly for 10 ohm, minus I into 10, then minus I into 15 equals to 0. Kirchhoff voltage लो से हम इसको इक्वल्स टू 0 लिख रहे हैं. नाउ यू कैन सोल्व फॉर आई विल बी इक्वल टू 12/30. Right? So this is a very simple circuit. Now we will solve one more question here. Determine the current in each branch of the network shown in the figure. So now in this circuit there are two batteries. First of all, if one 5 volt and one 10 volt. Suppose this current is I1, or say this current is I. If this current is I, then we can take this current I1 and this current I2. Right? This I current divides in two parts here, I1 and I2. Now I1 is going here, and suppose the current, this is I1. Right? Suppose in this branch current is going I3. Right? Here also this current is I. Here also suppose this current is I4, and in this branch suppose current is I5. First of all, Kirchhoff current law at node A. I equals to I1 plus I2. Right? So I2 can be written I minus I1. Similarly, apply KCL at B. I1 and I5 also coming. So I1 plus I5 equals to I3. Right? So I3 can be written I1 plus I5. Now we will apply KCL at D. So at D, this is I2. Sorry, this is I2. This I is written for this. So this is I2. I2 is coming, I4 also coming, I5 is leaving. So I2 plus I4 equals to I5. Right? I2 we already calculated in terms of I and I1. So I5 will be I minus I1 plus I4. Now at C, KCL at C. At C it will be I plus I4 equals to I3. So from here we can replace I4 equals to I3 minus I. So from here this I5 will be I minus I1 plus I3 minus I. So I and I will be cancelled. This will become I3 minus I1. Right? So now currents we know in all branches. First of all I1, second current we have taken I1, I2 we have taken I minus I1, current I3, current I4, this is I3 minus I, and current I5 is I3 minus I1. Now write the KVL, Kirchhoff voltage law. So first of all write the bigger circuit. This circuit, if we start from A, D, E, B, A. So if you write, now you have how many variables? I, I1 and I3. We have removed I2 I4 and I5. So we have 3 variable. So we need 3 equation. That means we have to write 3 KVL equations. So for bigger circuit, if we start from A and if we move in the direction of D, then we will write I minus 4 into I2. I2 is nothing but I minus I1. Then from D to E there is nothing. From E to B here is a battery and we are moving from low voltage to high, so it will be plus 5. Then from B to A there is a current I1 and we are moving in opposite direction, so plus 4 into I1. So this is the one equation. Now KVL in this loop A C B A. If we move from A to C, we are moving from high voltage to low voltage, that means minus 10 volt, moving opposite to the direction of current, that means plus 1 into I. Then C to B, moving opposite to the direction of current, so plus 2 into I3. I3 is I3. Then moving opposite to the direction of current, that means 4 into I1 equals to 0. This is the equation number 2. Now one more equation we need. So if we move in this circuit, we start from D, E, B, C, D. So from D to E there is nothing. E to B there is a battery moving low voltage to high, so that means plus 5. Then moving in the direction of current, that means minus 2 into I3. Moving in the direction of current, minus 2 into I4. I4 is here. I3 minus I. So you have 3 variable and 3 equations, so you can solve these 3 equations and you will find the values of current. Now we will study about cell. So what is cell? Cell is the device which converts chemical energy into the electrical energy, right? And cell is a source of constant EMF but not constant current, right? Now suppose in this we have filled electrolyte and there are 2 anode. If this is positive, this is negative, then this will be called anode and this will be called cathode, right? So electric current through this cell, this is the cell, through this cell will flow from anode to, and if we connect this with a resistor R, then current will flow in this direction. Inside the cell, current will flow from cathode to anode, right? But in this circuit, current will flow from this anode to cathode, right? This is R. Symbol for cell is like this. This and this one also. Here is internal resistance and it is the EMF of this cell, V is the voltage across the cell. So for a ideal cell, internal resistance will be 0. And now suppose this is the voltage, potential here is V plus and potential here is V minus. So we can say, if this is the cell, then we can say, first of all, if the circuit is open, first of all, potential, suppose this is A, this anode is A, this anode is B. So we can say VA minus VB. VA minus VB will be V plus minus of V minus. So this will be V plus voltage of potential of this will be in negative. So this is V minus, right? And this will be greater than 0, right? This is called EMF if the circuit is open. Right. Now if we connected a resistor in this circuit, then there will be a current I, and if we replace this in circuit form, then this will be like this. This is the capital resistance, external resistance, this will be the battery, and this will be the internal resistance R, and this will be the EMF of this cell. So if we write equation here and current is I, then we can write minus IR from KVL, minus I into small r plus E equals to 0. So from here E will be I into R plus R, or we can say current equals to E upon R plus R. So how we can find V? V is the voltage across this cell. So V will be equals to I into capital R, or we can say E minus IR, right? So value of I we know, so we can put this value, and this will become E into R upon I plus R, small r plus capital R. Now if so, what we have seen, how to calculate the voltage across the cell. Now if cell is charging, first condition is cell is charging, or we can say we are supplying the power to the cell. So suppose this is the circuit of a cell, this is internal resistance, this is EMF, and if this is charging, then circuit will be like this. Suppose this cell is charging, then how we will write the KVL? KVL will be plus V if we are moving from this point, plus V minus E, and current will be in this direction. We are moving in the direction of current, so it will be minus I into R. So V will be E plus IR, right? So when cell is charging, the voltage across the cell will be E plus IR. When cell is discharging, that means we are withdrawing the power from the cell. So suppose this is the circuit of, this is the external resistance, this is the cell with internal resistance R, current is I. Then we already seen voltage across the cell will be V equals to E minus I into R. Now suppose cell is in open circuit, so what will happen? If cell is in open circuit, that means there is no current, right? So E minus 0 into R, and we cannot apply this equation also because this is not a closed loop, right? So simply this V is equals to E. Why? Because there is no current in this circuit. Or we can say, if we connect a wire across this cell like this, so this condition is means cell is short circuit. So in this condition we can write current in this circuit is E upon R. So voltage across this will be, if we write from here, E minus IR, and if you calculate this, E minus I equals to E upon R into R, so this becomes 0. That means when the cell is short circuit, voltage across the cell will be 0. We can understand this by this logic also. Suppose this is a wire, connecting wires, and we assume in the circuit resistance of the connecting wires we can take 0. If at this point, if resistance is 0, that means if at this point voltage is V, then at this point voltage will be same. So we connected is 0 resistance wire here, that means the cell is short circuit. Now we will see the maximum power transfer in a cell. So we have seen, if this is the external resistance or this is cell, this is internal resistance. So what will be the current? Current will be the E upon R plus R. And what is the power in the this resistance, external resistance? Power consumed by this resistance will be I square into R. This will become E square R upon R plus R square. Now at what value of R the power will be maximum in this resistor, right? So what we will do, we will differentiate this with respect to R, and we will apply the dP upon dr. It will be E square is constant, square of denominator. So this become R power 4 and then R plus R whole square, differentiation of this term, this is 1 minus R as it is, differentiation of this will be 2 into R plus R, then differentiation of this 0 plus 1. So if you simplify this, you will find power equals, and this will be 0 for maximum. So dP upon dr will be 0. That means R square plus 2R into R minus multiply this, so 2r into r minus 2r square equals to 0. So this will be r square minus r square equals to 0. So we can say r equals to r. So power consumed by this load resistance will be maximum when this equals to internal resistance of the battery, and the graph between the power and internal resistance will be like this. This will be same when r equals to capital R. Now we will solve some simple questions. First is a battery of EMF 2 volt. So E is 2 volt, internal resistance is 0.5 ohm, a current of 100 milliampere, that means 100 into 10 raised to power minus 3 ampere. Find the potential difference across the terminal of the battery as the current flow through it. So this is the battery, and suppose current is I. So we can write I equals to E minus IR. No, not I. We have to find potential difference. So we can write V equals to E minus IR. V is the potential difference. So this is VA minus VB. This will be E minus IR. E is given 2 volt minus I is given 10 raised to power minus 1 or 0.1 into R is 0.5. So you can calculate this is 2 minus 0.05, that means 0.95 volt. Now in this question we can see in the previous question current, we are withdrawing the current from this cell. In this question we can see current is given this cell, that a battery of EMF 2 volt is given, resistance is 0.1 ohm given, and 5 ampere current is charging this cell. So potential difference will be, so we have seen in charging condition E plus IR. So you can apply voltage is, we have to find E equals to given 2 plus I equals to given 5, 0.1. So it will become 2 plus 0.5, that means 2.5 volt. Right. Now we will see combination of cells. First series combination. So in series combination cell will be connected like this. This is the first cell, this is the second cell, this is E1, this is R1, this is E2, this is R2. Similarly we can connect more cells, this is R3, like this. Suppose this is A, this is B, this is C, this is D. Now we have to find what is the equivalent resistance and equivalent EMF of these cells. So suppose equivalent EMF is E and equivalent resistance is R. And how we will calculate this? We can say VA minus VD equals to VA minus VB plus VB minus VC plus VC minus VD. Now VA minus VB is E1 minus, current will be same in all cell, suppose I. So E1 minus I into R1 plus E2 minus I into R2 plus E3 minus I into R3. And VA minus VD from this circuit, this is A and this is D, we can write E minus I into R. Current will be same. So if we compare these equations, then we will find E equals to E1 plus E2 plus E3 and I equals to, equivalent R will be R1 plus R2 plus R3. That means equivalent EMF for series combination will be the algebraic sum and equivalent resistance will be the sum of all resistors, internal resistors, right? Whenever you find internal resistance, you can simply add. Whenever you find net EMF for a series combination, you will put the values with sign. Now we will solve this question. So in this question we are given a battery having 6 cells of EMF 2 volt and internal resistance 0.5 ohm is charged by a 220 volt DC source using an external resistance of 10 ohm. Find the charging current. So these cells are charging by this source. Suppose the current is I. First of all, we can replace these all cells with equivalent EMF and equivalent resistance, internal resistance. So we can see all cells are in same direction. So 6 cells, so E equivalent will be 6 into E and R equivalent will be 6 into R. So this becomes, this circuit becomes like this. This is 6R and this is 6E. Current will be in every cell will be same because this is series combination. 220 current is flowing in this direction, 10 ohm, right? So now if we apply KVL in this circuit, then it will become, if we start from here, then it will become minus 10 into I plus 220 volt minus 6E. Value of E is given 2 volt and minus 6R into I. So I into 6 into R is given 0.5 ohm. So from here you can find the charging current. Now we will see the parallel combination of cell. So in parallel combination of cell will be connected to like this. Right, so voltage across all cell will be same here. So we can say, suppose this is A, this is B, so VA minus VB will be V. So V for cell 1 will be E1 minus R1 into I1, and V for cell 2 we can write E2 minus I2 into R2. This current is I and this will divide in 3 parts here, I1, I2 and here I3, right? So V equals to E2 minus I3 into R3. So here by KCL at this node, if we apply, then I equals to I1 plus I2 plus I3. And if we replace this circuit as a equivalent circuit, then we can say the equivalent if equivalent EMF is EQ and equivalent resistance is R EQ, then this becomes I becomes V minus the total resistance is total voltage across this equivalent circuit will be V, VA minus VB. So V minus so here equation will be V equals to E minus I into, we have taken opposite currents here, no? These are the charging currents for these circuits, right? Suppose the cells are in this direction, right? And here also. So V equals to E minus I into R equivalent. So from here I will be E minus V upon R equivalent, right? So this becomes E minus V upon R equivalent. This will be equal to I1. I1 will be V minus E1 upon R1, V minus E2 upon R2 and V minus E3 upon R3. If you simplify this is not V minus E1, E1 minus V. So here we will put a minus sign. So if you simplify this, then it will become E upon R equivalent will become E1 upon R1, E2 upon R2 plus E3 upon R3, and this will be minus V 1 upon R1 plus 1 upon R2 plus 1 upon R3, right? And if you further solve this, then it will become E upon R equivalent will be, if you take this equation this side, then it will become sigma E upon R minus V upon minus V into 1 upon R plus 1 upon R2 and so on, and minus 1 upon R equivalent, right? This equation will become like this. So from here we can see R equivalent. If we compare these two equations, so V is the common here and V is also here, so we can write 1 upon R equivalent equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus and so on. So 1 upon R equivalent can be calculated easily. Now E upon R equivalent. Now if I remove this part, if now I compare if this one and this equation, then this will become E equivalent upon R equivalent equals to sigma E upon R, right? So E will be, E is the equivalent, sigma E upon R multiply R equivalent, right? And if we write this equivalent for two equation, for two cell, then we can write equivalent will be, or you can remember this as in this form only, because this is easy to remember. E upon R equivalent equals to E1 upon R1 plus E2 upon R2 plus E3 upon R3, like this. So for parallel combination we have derived the formula 1 upon R equivalent will be 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on, and E equivalent upon R equivalent will be equal to E1 upon R1 plus E2 upon R2 plus E3 upon R3 and so on. So you can remember E equivalent upon R equivalent in this form. Now whenever you put the values of E1, E2, E3, then put the values with sign. Now in this question we are given E1 is 3 volt, E2 is 2 volt, E1 is 1 volt. R, this resistance is 1 ohm and these internal resistance are also 1 ohm. Find the potential difference between the points A and B and the current through each branch. So first of all, this is an open circuit, that means the current between I AB equals to 0, that means current is in this resistance is 0. So we can say, if this point is C, so we can say VA equals to VC. So VA minus VB equals to VC minus VB. First of all, we have to understand this, else we cannot calculate, because this is not a closed loop, so there will be no net current. Now if current in this is I1, in this I2 and in this I3, then the net current I1 plus I2 plus I3 is 0. That means at least one of the cell is charging. Now if we write I1, how we will calculate I1 will be, for I1 we will write VC minus VB equals to E1 minus I1 into R1, right? Similarly, VC minus VB equals to E2 minus I2 into R2, VC minus VB equals to E3 minus I3 into R3, right? So now if we replace this circuit, then we can replace like this. This is point A, this is external resistance, and this is the net EMF of this circuit. Suppose this is E and this is net resistance, internal resistance R, this is point B and this point is C. So net resistance will be 1 upon R equivalent will be 1 upon R1, 1 upon 1, 1 upon 1 plus 1 upon 1. This equals to 3. So R equivalent will be 1 by 3 ohm. Similarly, E equivalent we can calculate. So E equivalent upon R equivalent, that means E upon 1 by 3 equals to E1 upon R2, E1 upon R1, that means 3 by 1. Then E2 upon R2, that is 2 by 1, and E3 upon R3, that is 1 by 1. So this becomes 3E equals to 6, that means E equivalent is 2 volt. So this voltage VC minus VB is 2 volt. So if VC minus VB is 2 volt, then this current I1 we can calculate. We have to calculate the voltage VA minus VB. VA minus VB is E, because current in here is 0, that means VA minus VB equals to VC minus VB. So we have calculated potential difference between A and B, that is 2 volt. Now current I1. Current I1, from here current I1 will be, this is 2 volt, E1 is 3 volt minus I1 into R1, R1 is 1. So from here I1 is 1 ampere. Now from here I2 will be 2 equals to, E2 is 2 volt minus I2. So I2 will be 0. I3 will be, from here VC minus VB is 2 volt, we have calculated. E3 is 1 volt minus I3 into R3 is 1. So I3 will be minus 1 ampere. So values of I1, I2, I3 are, I1 is 1 ampere, I2 is 0 and I3 is minus 1 ampere. Minus 1 ampere, that means the direction of the current is opposite. So now in next question we have given, find the EMF and internal resistance of a single battery which is equivalent to this combination of 3 batteries. So first of all we will calculate this parallel combination, then we will calculate this series combination. So if we calculate this parallel combination, then R equivalent will be 1 upon R equivalent will be 1 upon R1, 1 by 2 plus 1 by 2, that is 2 into 1 by 2, that means 1 ohm. So R equivalent will become 1 ohm, and if we calculate E equivalent upon R equivalent, that is 1, E1 upon, we will consider this direction positive, so this will be negative. So minus 10 upon 2 plus 4 upon 2, so this becomes minus 5 plus 2, that means minus 3. That means this parallel combination will be like this. Negative minus, negative meaning means we have considered this is positive, so that means net EMF will be in this direction. So this is 3 volt and internal resistance is 1 ohm. So now this is a parallel combination, so E equivalent will be plus 6 and minus 3, that means 3 volt, and for internal resistance simply add, so 1 plus 1 is 2 ohm. So this can be replaced by a 3 volt battery with 2 ohm internal resistance. Now we will see mixed combination of cells. So in this, suppose in one branch there are n cells, EMF is E and internal resistance is R for every cell, right? And there are n cells in a one branch, and there are similar branches and number of branches are n. That means if we see this first branch, then first branch can be replaced like this, n into E, internal resistance will be n into small r, and these are m branches. Right, now the net EMF for this circuit will be, there are m internal resistance in parallel combination and each value is n R. So 1 upon R equivalent will be 1 upon NR plus 1 upon NR, and this will be written m times. So 1 upon R equivalent will be m upon NR. That means R equivalent will be NR upon m. Similarly, equivalent can be written. Equivalent will be equivalent upon R equivalent. Right, E1 upon R1, that is NE upon NR, and this similar equation will be written for m times. So we can say E equivalent upon R equivalent equals to m into E upon R. If we multiply by R equivalent, then it will become n into E. So E equivalent for this combination will be n into E, R equivalent will be NR upon m, right? So this combination can be replaced by NE NR by m internal resistance and NE EMF, and this is connected with this resistance R. Then simply we can say maximum consumed power by this resistance will be R equals to NR by M when this happens, right? This we already have seen, maximum power theorem. Now we will solve a question. N rows each containing m cells. How many rows? N. How many cells in series? M cells, right? Are joined in parallel. Maximum current is drawn from this combination in a 3 ohm resistance. So from this combination, a 3 ohm resistance, that means capital R value is 3 ohm, connected if the total number of cells used is 24 and the internal resistance of each cell is 0.5, then the values of M and N. Whenever the maximum power will be drawn, the current will be also maximum because P equals to I square into R. So the condition for maximum power and maximum current will be same, that means R equals to NR by M. This comes when N resistance were in series and M are the number of rows, but here it is just opposite, right? So this will become R equals to MR by N. First you have to observe this thing. So R is given 3 ohm, M into R is 0.5 upon N. This becomes 6N equals to M. Right? Now how many cells? 24 cells. In one series, M cells, right? And how many in one branch, how many cells? M cells. And we have how many rows? N rows. That means total cell will be M into N, that is 24. So solve these two equations and we will find the value of M and N. So here we will end this chapter, and in the next chapter we will study about electric devices.